Okay, so let me start with problem 1. So we want to know whether vectors are linearly dependent or independent. So we know that a set of vectors, v1 up to vk, is dependent, linearly dependent, if there are scalars c1 up to ck. Some of them can be 0, but they're not all 0, such that you have a linear combination c1 v1 up to ck vk equals the 0 vector. And independent means not dependent. So suppose we take the vectors in this set 2, 0, 0, 0, 5, 0, and 0, 0, 10. Let's call the first one v1 and the second one v2 and the third one v3. So suppose the 0 vector, which is 0, 0, 0 in R3, is a constant times v1, a constant times v2, and a constant times v3. So v1 is 2, 0, 0, v2 is 0, 5, 0, v3 is 0, 0, 10. If you scale or multiply and add, you get the vector 2c1, 5c2, 10c3. And that equals the 0 vector if and only if 2c1, 5c2, and 10c3 are 0. That is, coordinates of vectors that are equal. And 2, 5, and 10 are non-zero, so c1, c2, and c3 are 0. So the set of vectors is linearly independent. There's no linear combination of them that produces a 0 vector and has a non-zero coordinate. Let's see. Let me do, this is 1A. I don't want to do them all because I want to cover a range of problems. So let's look at 1D. So here I have the set of vectors 5, minus 2, 1, plus 1, minus 2, 5, and 1, 1, minus 4. And again, let me call this V1, V2, and V3 for simplicity. So suppose that the 0 vector is a linear combination of these. So that means C1 times the first vector, C2 times the second, and C3 times the third. So what are these vectors? If I multiply this by C1, I get 5C1 minus 2C1 C1. If I multiply this by C2, I get minus C2, 2C2, 5C2. If I multiply this by C3, I get C3, C3, minus 4C4. And then when I add, I get 5C1 minus C2 plus C3, minus 2C1. Oops, this is a minus 2 there. Minus 2. And this is a plus 1. I should do this correctly. This is 5 minus 2, 1, 1 minus 2, 5, and 1, 1 minus 4. So this is plus C2 here. So this is 5C1 plus C2 plus C3 minus 2C1 minus 2C2 plus C3 and C1 plus 5C2 minus 4C3. So we started with this set of 3 vectors, And suppose we have scalars C1, C2, and C3, such that this linear combination is the 0 vector. When you write out in coordinates, what is this linear combination? It's this. So C1, C2, and C3 are scalars for which these two vectors are equal. So the coordinates are equal. The first coordinate is 5C1 plus C2 plus C3 equals 0. The second coordinate is minus 2C1 minus 2C2 plus C3 equals 0. And the third coordinate is 5C1 plus 5C2 minus 4C3 equals 0. So C1, C2, and C3 are solutions to this homogeneous system of linear equations. So I have to solve a system of linear equations. I mean, that's how we started this semester, solving linear equations, because a lot of linear algebra reduces to that. So let's say I write the matrix of coefficients, 5, 1, 1, minus 2, minus 2, 1, 1, 5, minus 4. When it's homogeneous, I don't need to write down the 0 column, because whatever I do to the 0 column stays 0. So I could write it or I can leave it out. It doesn't matter. So let me put this matrix in reduced row echelon form. Let's say I interchange the first row and the third row. So I get 5, 1, 1, and 1, 5, minus 4. If I want to get a 0 here, I add 2 times the first row to the second row. 2 minus 2 is 0. 10 minus 2 is 8. Minus 8 plus 1 is minus 7. And if I want a 0 here, I add minus 5 times the first row to the third, or I subtract 5 times the first row from the third. It's the same thing. 5 minus 5 is 0. 1 minus 25 is minus 24. 1 plus 20 is 21. So I have 1, 5, minus 4. If I want to simplify things quickly, I can notice that the third row is minus 3 times the second row. So if I multiply this row by 3 and add to the third row, I get 0, 0, 0. And this is still the same, but if I divide by 8, I get 0, 1, minus 7 over 8. And then I want a 0 here. So I have 0, 1, minus 7 over 8, 0, 0, 0. And if I add minus 5 times the second row to the first row, I get 1 minus 0 is 1. 5 minus 5 is 0. Minus 5 times this is 35 over 8. 40 is minus 40 over 8. So this is minus, so this is what? Minus 5, 35 over 8, minus 40 plus 35, I think is minus 5 over 8. But this tells us that C1 minus 5/8 C2 is 0, C2 minus 7/8 C3, C3 is 0. So for any number C3, if I let C1 be 5/8 C3, C2 equals 7/8 C3, and C3 equals C3, this gives me a solution. So for example, the vector 5/8, 7/8, 1 is a solution. This is not 0. So you have non-zero scalars that satisfy this vector equation. So the answer is this set is dependent. It is not independent. Right, so this is what you do. You have a set of vectors. You look for scalars that give you a linear combination equal to the 0 vector, and you find non-zero scalars. Now, I know there's a mistake in here, so because I'm just checking. So let me just go through and double check everything quickly. I have my vectors 5, minus 2, 1, 1, minus 2, 5, and 1, 1, minus 4. So here's my matrix, 5, minus 2, 1, 1, minus 2, 5, 1, 1, minus 4, minus 2, minus 2, 1, 5, 1, 1, 1, 5, minus 4. That's okay. 1, 5, minus 4. Add twice this to this. I get 8 minus 7. Subtract 5 times this from this. I get minus 24. 21. Add 3 times this to this. I get 0, 0, 0. So I get 1, and divide this by 8. I get 0, 1, minus 7 over 8. So when I subtract 5 times this row from this row, the number that I get up here is minus 4 minus 5 times minus 7, 8 is plus 35 over 8, which is minus 4 is 32 over 8 plus 35 over 8. So this should be 3/8. So this is plus 3/8, and this is minus 3/8. Yep. So that's correct. Now, any questions about this? Okay. You'll notice on the review sheet there are a lot of proofs, because in linear algebra, once you get past certain calculations, there really are just a lot of proofs. So let's look at problem 2. So we're told that V1 and V2 are linearly independent, and prove that V1 plus V2, V1 minus V2 is also linearly independent. So the proof goes as follows. Let's say C1 and C2 be scalars such that C1 times V1 plus V2 plus C2 times the second vector equals the 0 vector. Of course, you expand this. This is C1 V1 plus C2 V2 minus C2 V1 minus C2 V2. And you collect the coefficients of the various vectors. This is C1 minus C2 times V1 plus, this is C1. C1 V1, C1 V2, C2 V1, C2 V2. So C1 minus C2 V1 plus C1 minus C2 V2, that equals 0, but V1, V2 linearly independent means these coefficients have to be 0, which means, let's see, C1 equals C2. And if you let C1 equal C2, then I have 0, which is C1 V1 plus V2 plus C2 V1 minus V2. But if C1 equals C2, this is C1 V1 plus V2 plus C1 V1 minus V2 is 2C1 V1, and CV2 minus CV2 cancels. So if 2C1 times this vector is 0, C1 is 0, so C2 is 0. And that's the proof. Questions about that? Problem 3, we're looking at the vector space R3. That's just ordinary three-dimensional space, X, Y, Z. Right? And in R3, W1 is the subspace generated by the vector E1, which is, oops, sorry, it's easier than that. I'm in R2. So I'm just looking at the plane, the XY plane, R2. And the vector 1, 0, that's just the unit vector in the X direction. That's E1. And W2 is the subspace generated by E2, which is the unit vector in the Y direction. This is E2. So what is the set of all scalar multiples of E1? It's just the x-axis. W1 is the x-axis. All multiples of 0, 1, W2 is the y-axis. So what does W1 intersect W2? Well, the x and the y axes just intersect at the origin, 0, 0, which is a subspace. The subspace consisting of just the 0 vector. What is W1 union W2? That's the x-axis and the y-axis and nothing else. So for example, so E1, which is 1, 0, is in W1. So it's certainly in W1 union W2. And E2, which is 0, 1, is in W2, which is contained in W1 union W2. But E1 plus E2, when you add these vectors, you get the vector 1, 1. The vector 1, 1 is over there. This is E2. That's the vector 1, 1. That's not on the x-axis. It's not on the y-axis. So this is not in W1 union W2. So W1 union W2 is not closed under vector addition. So W1 W2 is not a subspace. So that's a proof of that. Any questions so far?
No, that makes sense. Seeing the drawing for the intersection question makes sense. Something.
Yeah. Well, it's always good in mathematics when you can draw a picture, but you can't always draw a picture, but when you can, you're in good shape. Okay, let's look at problem 4. In part A, we have a basis for R3 consisting of the following vectors. V1 is 1, 2, 0. V2 is 3, 0, 4. And V3 is 0, 5, 6. Compute the coordinate vector for 1, 0, 0 with respect to this. So that means the coordinate vector of 1, 0, 0 with respect to this basis. So I write the vector and then I put in square brackets this, which means this is going to be the vector, let's say x1, x2, x3. What this means is 1, 0, 0 is this linear combination of the basis vectors. X1 times 1, 2, 0 plus x2 times 3, 0, 4 plus x3 times 0, 5, 6. So I have to solve this vector equation for x1, x2, and x3. If I scale or multiply and add, what I have on the right is the vector x1 plus 3x2, 2x1 plus 5x3, 4x2 plus 6x3. Which means I have to solve the equations x1 plus 3x2 equals 0, 2x1 plus 5x3 equals 0, 4x2 plus 6x3 equals 0. Again, this problem in linear algebra reduces to finding the solution of some linear equations. So if I write down the matrix of coefficients, 1, 3, 0, 2, 0, 5, 0, 4, 6, and I put this in reduced row echelon form, 1, 3, 0 is good, 0, 4, 6 is good. Take the first row, the second row minus 3 times the first. 2 minus 2 is 0, 0 minus 6, 5. Okay. Then just to make things slightly easier, 1, 3, 0. I'm going to interchange these two rows. Because then when I get this to be a 1, I have a small denominator. Divide this by 4, I get 0, 1. 6 over 4 is 3/2. And 0 minus 6, 5. So I want to get a 0 there, so I have 0, 1, 3/2. I take the first row minus 3 times the second. 1 minus 0, 3 minus 3, 0 minus 9/2. And 0 minus 6, 5. And then I want a 0 here. So I add 6 times this row to this row. 0 plus 0 minus 6 plus 6. 6 times 3/2 is 9. 9 plus 5 is 14. Oops. 6 times 6 minus 6 is 0. That was the whole point. And 0. And then if I divide this row by 1 over 14, let me just do it quickly. I get a 1. So sorry, I made a terrible mistake. This vector isn't 0, 0, 0. It's equal to 1. This is x1 plus 3x2 is 1. So it's an inhomogeneous system. So I need a 1, 0, 0 here. 1, 3, 0, 1, 2, 0, 5, 0, 0, 4, 6, 0. Okay. So 1, 3, 0, 1. I added minus 2 times this to this, I got 0, minus 6, 5, minus 2, and 0. I interchange 0, so I get 0 and minus 2. Then this is 0, 1, 3, 0, 1. Dividing this by 4 is still a 0. And this is still a negative 2. And I add 3 times this row to this row. Sorry, minus 3. I get 1 minus 0, 3 minus 3, 0 minus 9 halves. Minus 3 plus this is still a 1. This is still a 0 here. 6, 5 minus 2. Then this is 1, 0. And then I add 6 times this row to this. And this is 14. And it's still minus 2. And then I have 0, 0, 1, minus 2. I multiply this row by 9 halves and add to the first row. I get 1, 0, 0, minus 9 plus 1 is minus 8. Oops. Minus 9 times this. 9 times this is minus 18 plus 1. It's minus 17. And if I add minus 3 halves times this to this, I get 0, 1, minus 3 halves plus 3 halves. Minus 3 halves times minus 2 is 3. So if this is correct, x1, x2, x3 is equal to the vector minus 17, 3, minus 2. So let's see whether that's correct. Minus 17, oops, plus 9 isn't right. So this is all done correctly, except I made mistakes. So let me go back and check it again. That's just how you do mathematics. You check. 1, 2, 0, 3, 0, 4, 0, 5, 6. 1, 2, 0, 3, 0, 4, 0, 5, 6 equals 1, 0, 0. So 1, 3, 0, 1, 0, 4, 6, 0. Minus 2 is minus 6. 5 minus 2 is minus 2. Switch around. Instead of 1 minus 2, 0, 1, 0 minus 2. 1, 3, 0, 1. Divide by 2, divide by 4. 0, 1, 3 halves, 0. Minus 6, 5, minus 2. Take the first row minus 3 times that. I get 1, 0, minus 9 halves, 1. Add, so 1, 0, minus 9 halves, 1, 0, 1, 3 halves, 0. Add 6 times this row to this. I get minus 2. 6 times 3 halves is 9. Plus 5 is 14. 14. Okay. Then divide, oops, is that right? 6 times this plus this. 9, 14, and minus 2. So this becomes 0, 1, 0, minus 9 halves, 1, 0, 1, 3 halves, 0, 0, 0, 1, minus 1/7. When I divide by 14. So if I add 9 halves times the third row to this row, I get 1, 0, 0. 9 halves times this is minus 9 over 7 plus 1 is minus 2 over 7. And minus 3 halves plus this. So minus, minus 3/2 is 3/14. So in the unlikely event that this is correct, I get minus 2/7, 3/14, minus 1/7. Or if I like, just to have whole numbers, it's 1/14 times minus 4/3 minus 2. So let's see if this is correct. X1 minus 4 plus 9. So there's still some arithmetic mistake in here, and I don't want to spend more time on it, but I'll figure it out and correct it. But in any case, that's the method. Method is always the method. What about for C?
Wouldn't 4C be the same concept of what you just did?
They're all the same. The method is always the same. Oh, sorry. So part A I skipped. That's just to prove those three vectors are linearly independent. So that's the same as the problem 1, and part C is the same as problem 2. So let me actually do the problem 5 because that's different. So we have subspaces of Rn, W1 contained in W2 contained in Rn. So if the dimension of W1 equals the dimension of W2, what does this mean? Let's say it's equal to K. So W1 has a basis with K vectors. And if W1 is not equal to W2, I mean, here's our picture. Here's W1, and it's sitting inside W2, all contained in some vector space. If W1's not W2, then you can find a vector U, or a vector W, I'll call it. Then there exists a vector W in W1 such that a vector in W2, which is not, this means not in W1. If W1's a proper subset of W2, there's a vector in W2, not in W1. Call it W. So we proved the lemma that says if you have a linearly independent set and it generates a subspace, W1, and you take a vector not in that subspace, those K vectors in the original basis together with W are linearly independent. And this is contained in the bigger space W2. Let me just call this W1. And we also proved if you have a linearly independent subset of a vector space, you can add vectors to get a basis. So then there exist vectors W2 up to WL such that V1 up to VK and W1 up to WL, this is a basis for W2. So the dimension of W2 is the number of vectors in the basis. This is K plus L, and L is at least 1. There's at least one vector there. So this is greater than K, which is the dimension of W1, which is a contradiction. Because we said, and we started out by saying, suppose the dimension of W1 equals W2. If the vector spaces are different, you get a contradiction. So therefore, dimension of W1 equals the dimension of W2 implies W1 equals W2. And the converse is trivial because if W1 equals W2, a basis for one is a basis for the other, and they have the same dimension. And that's the proof. What about problem 6? So now we're in R3. So this is the x-axis, the y-axis, and the z-axis. Where are the vectors 1, 0, 0? That's a unit vector in the x direction. What's the vector 0, 0, 1? So this would be the vector 1, 0, 0. This vector would be 0, 0, 1. It's a unit vector in the z direction. And if I take linear combinations of these, I get all vectors x, 0, z. I get all vectors where the y coordinate is 0. So geometrically, this is the subspace generated by the vectors 1, 0, 0 and 0, 0, 1. It's what we would call the xz plane, this infinite plane. Where is the vector 1, 1, 0? So sitting in the xy plane, if you go one unit in the x direction and one unit in the y direction, you end up over here. This is the vector 1, 1, 0 in the xy plane. So I have this vector in the xy plane and this vector in the xy plane. And all the linear combinations is just the whole xy plane. Subspace generated by 1, 0, 0 and 1, 1, 0. Well, really, you get all vectors x, y, 0. That's the xy plane. What is the intersection? Oh, sorry, there's a mistake in this. So, but the intersection, W1 intersect W2, where does the xz plane and the xy plane intersect? It intersects in the x-axis. Now, one-dimensional space through the origin. So this is W1 intersect W2. And for part D, I should have said, consider the subspace generated by these three vectors, 1, 0, 0, 0, 0, 1, and 1, 1, 0. And that's everything in the xy plane, and then you go up and down. It's all of R3. So the dimension of W1, that's the dimension of the XZ plane is 2. The dimension of W2, that's the XY plane, that's 2. The dimension of W1 intersect W2 is the dimension of the line, which is 1. And what I should have said is the subspace generated by W1 plus W2. And that's equal to R3. The dimension of W1 plus W2 is 3. And you look at this plus this equals this plus this. 2 plus 2 equals 3 plus 1, which is true. And that's a special case of the equality of dimensions that relate to subspaces of W1, W2, the sum and the product. Now, all of the proofs are in the notes. And let me just do the last two problems because they're calculations that are important to be able to do. So, for example, problem 12 is the proof of the most important theorem about linear transformations, which I proved already 3 times in classes. Let's look at problem 13. So A is the matrix 2 minus 1 minus 4, 2. And T sub A is the linear transformation from R2 to R2 defined by T sub A of a vector xy is just the matrix A times xy. If I want to write it out, T sub A of xy is A times xy. A is the matrix 2 minus 4 minus 1, 2 times xy. When I multiply the matrix times the vector, I get 2x minus y minus 4x plus 2y. So this is explicitly the linear combination. And the kernel of T it's all vectors xy such that T sub A of xy is the 0 vector, which means all vectors xy such that this is equal to 0. Which means x and y are solutions of a system of equations. 2x minus y equals 0, minus 4x plus 2y equals 0. And you can solve this with a matrix or any other way, but you see this equation is minus 2 times this equation. So the solution is any y equal to 2x. So any vector of the form x, 2x, or x times the vector 1, 2. So the kernel of this linear transformation is the one-dimensional subspace spanned by the vector 1, 2. So that's the kernel. Well, this is the subspace. So the nullity of T is the dimension of the kernel, which is 1. What is the image of T? The image of T is all vectors 2x minus y minus 4x plus 2y for any numbers x and y. But if you look at this again, you see that the second coordinate is always minus 2 times the first coordinate. So I could say for any number t, if the first coordinate is t, the second coordinate is minus 2t. So this is a set of all scalar multiples of the vector 1 minus 2. And the rank of t, which is the dimension of the image, is 1. So the theorem says the dimension of the vector space is the nullity plus the rank. And in this case, the nullity is 1, the rank is 1, because that's, and 1 plus 1 is 2. So we can verify the theorem by knowing that 1 plus 1 is 2.
Professor,
Yeah.
you see how when we're multiplying the 2, -1, -4, 2 by the x and y, is it supposed, like I've been writing it 2x minus x and then minus 4y plus 2y. Is that wrong? It should be like you multiply the x.
This matrix times this vector
Yes.
is 2x minus y minus 4x plus 2y.
Okay, so the x should be applied to the first numbers and the y should be applied to the second numbers. Because I was doing it like
Yes.
I thought. Okay, got it. Thank you.
Because really, if you multiply a vector times a matrix times a vector, this is really x times the first column plus y times the second column.
Yeah.
Is exactly that.
Awesome. Yeah.
But no matter what, that's the answer.
Okay. Thank you.
Yep. Let me try and do number 14. So I have the matrix A, which is 1, 2, 3, 4. And if I multiply this by the vector xy, I get x plus 2y, 3x plus 4y. So, so this is my t sub a of xy. Right? It's the linear transformation that comes from this matrix. And applied to a vector xy, this is what you get. So what is the kernel? So xy, this vector, is in the kernel of t. If and only if this is the 0 vector. X plus 2y equals 0. 3x plus 4y equals 0. So I have to solve these two equations and two unknowns. And, again, any way you like, 1, 2, 3, 4 is 1, 2. This minus 3 times that is 0. This minus 3 times that is minus 2. Divide this by minus 2. Let's get rid of this. So the only solution is x and y equal the 0 vector. So the kernel is just the 0 vector. And the dimension of the kernel, which is the nullity, is 0. The dimension of the trivial vector space consisting only of the 0 vector is always defined to be 0. What is the image of T sub A? So it's all vectors, x plus 2y, 3x plus 4y for all possible choices of the scalars x and y. So we can say that a vector, I don't know, rs is in the image of t sub a if and only if x plus 2y, 3x plus 4y is rs. Or if and only if you can solve the equations x plus 2y equals r, 3x plus 4y equals s. So when can we solve this inhomogeneous system? I'll write down the matrix. I mean, there are other ways, but even quicker maybe, but subtract 3 times the first row from the second. I get 0 minus 2 s minus 3r. So I get 1, 2r, divide this by minus 2, 0, 1, 3r minus s over 2. Minus 2 times this row plus this row. 0 plus 1 is 1, minus 2 plus 2 is 0. Minus 2 times this is s minus 3r. I get s minus 2r. So what this says is, if I let xy be equal to s minus 2r and 3r minus s, then t sub a of xy is rs. So the image of t sub a, it's all of R2. And so the rank is equal to 2. And that's the story.
Okay, so why is the rank equal to 2?
Because the image of T sub A is R2. And the definition of the rank is the dimension of the image of the linear transformation. And the dimension of R2, so the rank of T is the dimension of the image of T. That's the definition of the rank of a linear transformation. But the image is all of R2, and the dimension of R2 is 2.
Okay, thank you.
I mean, there's a different definition of the rank of a matrix, but it turns out if you interpret a matrix as a linear transformation, then you get, it's always exactly the same number. Okay. All right, that is it for the morning. I will be back at 3 o'clock. No, sorry, 4 o'clock. Any
Thank you.
questions before I stop?